Hello everyone. Today we'll study with the next module. It's actually module 5 according to the new syllabus. So module 5, arches and cables. So in this module, it's divided into two parts. One is you'll be studying about the arches, unit 1, and unit 2 is about cables. So first let us study what is an arch. So basically an arch is a curved beam itself. Okay, instead of it's a curved beam, and it can be used when the beams are of longer spans, where you want to have a beam. You have to provide a beam which is of long span, and at the same time you have to control the bending moment also. Longer the span, obviously the bending moment would be larger. But in order to control the bending moment, that means you have to uh, provide a longer span. At the same time, bending moment also should be lesser. So to fulfill these two criterias, so the same beam which is now straight becomes like an arch. So that is called as an arch. So in this arch, we are going to study what are the different types of arches, and what are the different loads acting on the arch, and then what are the how to design an arch, and where would be the maximum bending moment and shear force. Obviously wherever the maximum bending moment is there, at that portion you have to provide more steel. Okay, so with this background, so first arch is basically so arches are the curved beam itself, and they are used when you want to provide beams of longer spans with reduced bending moment. Okay, so there are two types of arches when you classify them according to the shape. So one is parabolic and the other is semicircular. So in parabolic arch, the load gets uniformly distributed, and there exists only compression force only. Whereas in semicircular arch, they're again uniformly loaded, but then here there are two types of stresses, or two types of stresses actually taking place. One is the flexural stress. Flexural stress means it's a bending stress. The other is compression stress. So for your syllabus, you'll have only parabolic arch, wherein you'll come across only the compression forces, and these compression forces will act at the support. Okay, now let us study in detail. So there are so now the arches are again classified into three types. So there is three hinged arch, two hinged arch, and zero hinged arch. Now this classification is based on the supports which are provided here. So that's why it's called as hinges. You can see here the name itself indicates it's three hinged arch. So one hinge here, second hinge here, that is the support, and the third hinge would be at the crown. So this is called as a crown. You can see this zenith point, that is topmost point here, that is called as the crown. Okay, this is called as a crown, and the distance between two supports is called as the span, and this height, that is the vertical distance, is called as the rise. Okay, so they'll be using these three in the question. They'll be using these three terminologies only. So they'll give the span, they'll give the rise, and also at times they give you the crown height also. So you can see here, so these are hinges. Okay, so again, hinge support has only two reactions, that's why it's called hinge. So here also it is a hinge. Okay, it is hinge at the crown to stop. So 1, 2, and 3, that's why it's called as three hinged arch. Now three hinged arch are statically determinate. So statically determinate means the number of unknowns are lesser, equations of equilibrium are more. Okay, and then two hinged arch. Now you can see here one hinge, two hinge. So there are only two hinges. So this is called as two hinged arch. What we used to call it as supports now becomes the hinges here. We've used this terminologies before for supports. When now it becomes hinges. So it is one hinge, two hinge. So that's why it's called two hinged arch. So this is called as the rib of the arch. This is the span. Again, the distance between the two vertical hinges. Two horizontal hinges are called as span, and the vertical distance is called rise. You can see here, it looks like this actually. So what we are drawing here is it one dimensional. So in actual, it looks like this. So the beam, if you try to invert this, it looks like an arch. Then this is the zero hinged arch. That means you can see here, there is absolutely no hinges at the supports. Both the supports has fixed. You can see here, both supports have fixed support only. That's why statically indeterminate. That means number of unknown forces here, 1, 2, 3. Horizontal, horizontal, vertical moment. So they are more compared to the equations of equilibrium. Equation of equilibrium only 3. So that's why it's statically indeterminate. Okay. So now for your syllabus, we have only 3 hinged arch plus they should be parabolic. So it's 3 hinged arch in combination with parabolic arch. Okay. So now let us just solve this. Let us see what are the different parameters coming here. So first, 3 hinged arch are basically determinate structures, and they are internal stresses induced in it. Now you can see here, consider a 3 hinged arch. So you can see here A, B, and this is C. Okay, it's 3 hinged. 1, 2, 3. 3 hinges arch. It is subjected to, see here, two types of forces are there. So P is the load. Okay. Now, if you see at A and B, there are two supports. At A and B, there are two supports, and they become the hinge support. Now, because they are hinge support, so in hinge support we have two reactions. One is horizontal, vertical, horizontal, vertical. So these are two supports, and with the reactions, and this is the hinge support. So basically now the end supports has four reactions, 1, 2, 3, 4. Okay, so what we'll do here, but the equations of equilibrium are only 3. So what we do here is, see here, there are 4 unknown support reactions, 1, 2, 3, and 4. And 3 unknown reactions can be found out using 3 equations of equilibrium. That is summation h is equal to 0, summation v is equal to 0, and moment about A is equal to 0. So if using 3 equations, we can find out. So, but we have one more fourth reaction here. So that fourth reaction, what we'll do is, we'll find the moment about this point. That is, we'll find the moment about crown hinge. So when you have 4 uh, unknowns, we can solve using 4 equilibrium equations. So that's why it becomes a statically determinate structure. So you'll find summation h is equal to 0, summation v is equal to 0, and moment about A is equal to 0. These are actually the 3 equations of equilibrium. But we have unknown 1, 2, 3, 4. So the fourth unknown, what you're going to find out here is, we'll find moment about this point. So this is how it becomes a statically determinate structure. Now, we are only dealing with parabolic arches because that is only there for the syllabus. So with this parabolic arches, we come across finding only the y ordinate. So you can see here, this is length L, and if I cut this section anywhere here, when I cut this section, so I'll name this as section 1, 1 at a distance x from end A. So obviously I have to find out at what distance is this placed. So x horizontal distance, I'll take it as x, and vertical distance, I'll take it as y. I know exactly at the center, that is L by 2, it is h. But I want to know at any other distance between these 2 points here, between A and this crown hinge. If I want to find this height, I'll name it as y. So if you want to find the y ordinate in this parabolic arch, so it would be y is equal to 4h L x. So again, see here, 4h means height h. Okay, L into x. So this is L into x distance minus x square divided by L square. Okay, now how would we got this equation? I think in maths you have already used this equation when you're in mathematics, like maybe in M4 you've used this equations. Again, deriving this equation is not important. because we are using this equation. Okay, directly you can use this equation. So it is a parabolic arch. So take this y ordinate and you can solve this. So whereas x is the horizontal distance measured from the end. Okay, of course. This is not there for your syllabus. It is semicircular arches and segmental arches. Okay. Now we have two different terms here. That is, one is normal thrust and the radial shear. Okay. Now see here, normal thrust, we are using the letter N, and radial shear Q. Now let us try to understand what is this normal thrust and radial shear. You can see here. Okay. Now this is a parabolic arch. Okay. Now what I'll do, I'll cut the section like this. See, it is a two-dimensional. I'm taking the complete section here, x and y. So I'll cut the section here, xx across. So I'll take only this parameter, only this left side of the figure, and I'll just show it here. And so here, okay, now to be more specific, I'll use this diagram here. To make things simple, within the beam, I've just shown this xx. I'm going to cut it across. So this is xx axis and vertical axis would be yy. Okay. This is, I'm drawing along the beam here, along this length of the beam, arched. Okay. So now you can see here, this is y and this is x. It is tilted. Now, with respect to this x axis, this is normal. This is called as normal thrust. Okay. So see here, remember, normal thrust is nothing but it is the force which is acting perpendicular to the surface. So wherever I cut the surface, see here, I've cut the surface here. It's like this. I've cut it here. So normal is nothing but it will always act perpendicular to the cut surface, and radial shear will always act parallel to the cut surface. Okay, so that's why normal thrust, normal means always perpendicular force, and Q, radial shear, means always parallel force. This is how you can remember. Normal is perpendicular and radial shear is parallel to the cut surface. Okay, so now because this diagram becomes little tedious for you to understand, these things become simple if you just look at here. Of course, here also it is same. See here, normal N is the normal which is acting exactly at this x-axis, and Q is acting parallel to this cut axis, and this is angle. See here, angle theta. So theta is nothing but it is the, we read x and y like this. According to us, we read it exactly the straight. Now because it is slightly tilted, that this is the cut axis now. So this angle between the inclined cut surface and the straight surface is nothing but theta. That's how it is N. We'll use it here. As here, when you're finding this vertical and horizontal forces, so normal thrust N, if you want to find out this, it is nothing but V sine theta. You can see here, this is V sine theta plus H cos theta. Of course, again, this derivation is not important. Only how to use this and what is this N and Q is important. So if you want to find N, it is V sine theta plus H cos theta, and Q, that is radial shear, is V. It is just the opposite. See, V remains, V and H remain same. Sine becomes cos, cos becomes sine, plus becomes minus. This is how you have to remember this. Okay. So normal thrust is the force which is acting exactly perpendicular to the surface, and radial shear is acting parallel to the surface. Okay. Now there are steps, series of steps to find out. So you can see here, produce. Okay. First it is, okay, radial shear. Then is, okay, we have to find procedure to find out bending moment, normal thrust, and radial shear for a three-hinged parabolic arch. So bending moment means M, normal thrust means N, and radial shear Q. You have to find all three parameters for three-hinged parabolic arch. So the first thing is, again, sketch three-hinged parabolic arch with the given data, and then find the reactions due to the external loads. Calculate the bending moment mx at xx for external loading. Then compute the vertical ordinate y of of an arch, which would we have the formula, which you've already seen this. This is for a parabolic arch. And then find the horizontal thrust by taking moment about the center and the crown. Then find the resultant, r is equal to h square plus v square, and followed by the angle theta. And then find the maximum bending moment, that is positive bending moment, negative bending moment. And then once you find bending moment, you will find normal thrust and radial shear. So with this series of steps, let us start with the problem. Okay, so in the first problem, just read again in the exam. They'll not give you the figure. They'll just give you a four-lined question wherein they'll give all the detailed data. You yourself have to draw it. Okay, so a three-hinged parabolic arch of span 24 meter, rise 6 meter, with hinges at abutments and crown points. Arch subjected to a point load of 50 kilonewton and 150 kilonewton at a distance of 8 meter and 20 meter from left support. So again, they have given you everything in this. So from this data, you have to draw the arch. Okay, and then find reaction at the support, resultant reaction and its inclination at the support, draw bending moment diagram, normal thrust and radial shear at a distance 6 meter from the left and right support. Okay, now you can see here, it's a 3-hinged parabolic arch of span 24 meter. You can see here, I've shown here 1, 2, 3, 3 hinges. So A, B would always, see again the pattern should be like this only when you're naming it. A should be first support, B should be second support, and C is the crown hinge. Okay, C. And they've told the length of the span is 24 meter, and the rise is nothing but this. Height is 6 meter, and arch is subjected to a point load of, okay, now see here, from the left support they have told. So from the left support at 8 meter it is loaded, that is 50 kilonewton, and again from 20 meter it is 150 kilonewton. So you have to draw this very thoroughly and carefully. Now see here, exactly at this complete length is 24. So first split this, exactly half of the distance is 12 meter. So this point between A to C at this point, horizontal distance is 12 meter. And then you have to place this accordingly. See, always you have to show the loads at the top only. Okay, at the top of this point C. So from here at 8 meter, it is 50 kilonewton. Again from the same point A, it is at a distance 20. So this is 20. Now you can see here, exactly half is 12. So it is 8 is at this distance. Exactly half is 12 meter, and 20 is this portion. And of course, last point would be 24. Okay. Then find, first thing what you have to find is reaction at the support. So first we'll find the support reactions. Now you can see here, again, A and B, they are hinge support always. It's a 3-hinge parabolic arch. So it is a support. It has a support here, hinge support. So at A. So now what we'll do is we'll name this as HA, horizontal force at A, vertical force at A. Okay. So HA, VA, HB, VB. Okay. So now I'll just show all the reaction forces acting here. Then as usual, we'll use the equations of equilibrium. Okay, first, so again the order could be anyhow, summation H, summation V, and moment about A. Okay, so I'll use the moment about A first. So sum of moment of forces about A point. So you can see here VB. Now VB, again moment at A, clockwise positive, anti-clockwise negative. All the clockwise moments are positive, anti-clockwise moments are negative. So VB. Now VB is going in anti-clockwise direction. So VB into this distance 24. Then from this point 150 into this distance 20. So it's going clockwise. Next 50 into this distance 8. Again it is going clockwise. Okay. Now HA will not act. Okay, this force HA and VA will not act because you're finding moment at A point itself. And similarly, HB also will not act because it is acting on the same line of action. So there is no moment created. So find out VB. So once you find out VB, then we have the second equilibrium equation, that is summation V is equal to 0. Okay, that is all the forces, vertical forces should be equal to 0. So you can see a VA plus VB. There are two vertical forces upward, 50 and 150 downward. So add these. So you'll get, we have already found out VB. So substitute this value and you'll get VA. Okay. Next, third one, that is summation H is equal to 0. Summation H. So see here, HA is acting to the right plus HB is acting to the left. So minus is equal to 0. But still, see here, HA and HB. I use the third equation. In spite of that, we didn't get the HA and HB are still unknown. So now to find out this, what we'll do, we'll find moment about C. So that is moment about the crown hinge. Because here, taking moment about C, that is sum of moment of forces about C is equal to 0. Okay, now you can see either to the left of C or to the right of C. The choice is yours. Okay, so in this portion you can consider CB. Okay, now when you're choosing here, when you're choosing left or right, you should choose them wisely because you have to take the sign conventions also properly. Okay, all right, so you can choose anything. So if I choose to the right side here, again clockwise positive, anti-clockwise negative. Okay, so VB, again it is going in anti-clockwise direction. So VB into half the distance at C. So it is 12 plus HB. HB check. HB is going clockwise. So HB is HB into height. Now this is horizontal into vertical. So HB into 6. Next, 150 into this distance. Okay, this is 20 minus 12 is 8. So 150 into 8. Okay, this is how you solve this. So now you got VB, VA, HA, HB. Now you can see here. Once you find HB, if you put back in this equation, you'll get the value of HA. So HA and HB would always be same. HA and HB would always be same because left side force should be equal to right side force. Only then it will be set to an equilibrium. Vertical forces will be balanced by vertical reactions. Horizontal thrust, so it's called as horizontal thrust, will be balanced by left side, will be balanced by right side. Okay, so we found out the reaction now, all the four unknowns. Next, we have to find the resultant. Now, to find the resultant, we know that RA, if you want to find resultant RA, it is HA square root of HA square plus VA square. So solve this, you'll get this. Then theta A is nothing but VA divided by tan inverse of VA divided by HA. Similarly, RB, if you want to find RB, it is same, HB square plus VB square. Solve this, you'll get this. And then you'll find theta B. Next, to find out the bending moment. Okay, so my main intention is to find out the bending moment and then normal thrust and radial shear. So now if you want to find bending moment, so we know that bending moment at the hinge support would always be 0. There is bending moment at A, bending moment at B, and bending moment at C, because these are three hinges. So bending moment at the support hinges would be always 0. That's what we have written here. Okay, now we know that we already have uh, the equation of an arch, parabolic arch. So equation of a parabolic arch is y is equal to the 4h lx minus x square divided by L square. Okay, now what we'll do is we have to put back all the equations here. We'll substitute all the in this, we'll put back all the equations in this and then solve this. So you can see here, first h is rise, so 4 into rise is 6, 24, L is length of the arch, 24. Now this x is like a variable, so you can find from 0 to 24 at any distance. You can find y ordinate. You can cut this section anywhere across. So anywhere across it is, if you cut at x, you can find y. Wherever you cut, you will get y. So that's how we'll keep it in the equation form only, and that is in terms of x. So L, that is 24 into x minus x square divided by L square, that is 24 square. So solve this, okay, then keep it in terms of like that only. So you can see here, solve this and keep it. It is like 1x minus 0.0416 x square. Now always you have to keep this in equation form. Okay, now how to use this equation is here. For any value of x, you will find the value of y. Y is always dependent on x. Okay, now let's check this out. Now we know that bending moment would be maximum, of course, at this load points. So at A, C, B, it is 0 because they're hinges, and at bending moment at the load points would be maximum. So I know the load point now. So with respect to A, now it is acting at a distance 8 meter. So 50 kilonewton is acting at distance 8 meter. Okay, so now bending moment at 50 kilonewton, that is x is equal to 8 meter from the left support. So what I'll do here is I'll put it back in the equation. So y is equal to, instead of x, I'll put value of x, that is 8, and I'll solve this again in this value of x, 8 square. So at a distance 8 meter, the y distance would be 5.33. That means here at a distance 8 meter, y would be 5.33. Okay, that is what we have got here. 5.83. Okay, 5.33 is y. So now bending moment at this point would be, okay, now see here, bending moment at this portion. So again, at this meter, see at the left side, check how many forces are acting. Okay, at the left side, how many forces are acting. So at a distance 8 meter, okay, first 58.33 into perpendicular distance, that is 8. Then h is 83.33 into y distance, that is just now we have found out 5.33. And at 8 meter, this 50 kilonewton is acting. So with respect to this here, 50 kilonewton, left side only 2 forces are acting. So we'll be considering only 2 forces here. So 58.33 into 8 clockwise, so positive. Then this is going anti-clockwise, that is 83.33 into this distance, anti-clockwise. So sum this up and find out how much is the bending moment. So it is 22.49, that is at a distance 8 meter because of 50 kilonewton load. Next, similarly, calculate the bending moment at 150 kilonewton. Okay, now see here, bending moment at 150 kilonewton. Again, 150 kilonewton. So you can see to the left side or to the right side. So again, if you see to the left side, there are many forces coming across this point. So what we'll do to make things simple, with respect to this 150 kilonewton, I'll see to the right side. I'll see the forces only to the right side. So right side, anti-clockwise is positive, clockwise is negative. Okay. So now see here, 150, it is acting at a distance 4 meter. With respect to left support, it is 20 meter. With respect to right support, it is 4 meter. So here only I'll be considering these two forces now. VB into 4, HB into this distance. I'll find out first how much is this distance. Okay. So now we can see here bending moment at 150 kilonewton, that is at x is equal to 4 meter from right support. Okay. So again, we have already found out this equation. So we have to only substitute the value of x here. So y is equal to, instead of x, put this 4 minus, again 4 square. So you'll get 3.33. So at a distance 4 meter from right support, y is 3.33. And you can notice here below 150, always this h at the center, it would be maximum. And when it reaches the support, the y distance goes on decreasing. Okay. So now again, find the bending moment now. So VB into 4, again, see VB into 4. So right side anti-clockwise is positive. Then this is HB minus HB into this side, that is 3.33. Okay, so now we got the bending moment at 150 kilonewton and 50 kilonewton. We have found out. So bending moment. Now, once you found out this bending moment, you have to show it here in the diagram. So how to draw this diagram? See, first as usual, just draw the arch like this. Show the length here. Draw the arch. Show the points A, B, C. Then mark this points. That is, wherever the load is acting, just mark those points. This L is equal to 8. Here L is equal to 4 and total length is 24. Okay. Now below this load point, mark this point. Okay, see, this is like your zero line. Okay, so it should start at A, maximum would be at load, and again it has to, at C it has to become 0. Okay, again it has to meet here, C. Then similarly, again from 0 point, it should go maximum 283 at L is equal to 4 meter from right end, and again it has to reach back to B. So this is the bending moment diagram now. Okay, once you draw the bending moment diagram, next is you have to calculate the normal thrust and radial shear. Okay, now they've asked to find out normal thrust and radial shear at a distance 6 meter. Okay, calculate normal thrust and radial shear at a distance 6 meter from the left support. Only from the left support you have to find out. Okay, so now to calculate this, we are more again interested in y. Now if you want to use it y is nothing but it is the vertical ordinate. That is the equation of a parabolic arch, which we have already found out. Okay, so here it is always like this. If you want to find normal thrust and radial shear, you see here A is the point. Okay, and this is the arch. Okay, what we're doing here is we're just cutting this portion here, and at A just mark all the forces first. Mark the forces. So HA we have already got, that is 83.33, and V A is 58.33. Mark this point. Now this is the arch here like this. Okay, now you have to complete this triangle. So to complete this triangle, vertical force, just draw a vertical line and a horizontal line. So this is nothing but the angle theta. Okay, so dx is nothing but it is a small cut portion dx in x direction, and y is dy, vertical distance in y direction. Now to keep this in equilibrium, okay, now check this out. Between A to, see here, A and next load point is at 8 meter. So 50 kilonewton is acting at 8 meter. But we are finding at within 8 meter, that is at a distance 6 meter. So from 0 to 6 meter, there are absolutely no loads acting here. So whatever load is acting here, the same load will be balanced here. Okay, now check this out. Okay, at A, there are two loads acting. So at a distance 6 meter, there are absolutely no loads. So whatever vertical and horizontal forces are acting at this portion, to maintain the equilibrium, the same forces will be acting equal and opposite. Now check this out. 83.33 kilonewton, right side. To stop this, there is 83.33 to the left side. So it is in equilibrium, horizontal. Likewise, vertical, 58.33 upward. To stop this, 58.33 downward, because there are no loads acting between 0 to 6 meter. So things become simple. Okay, so now you can see here tan theta. So tan theta is opposite by adjacent. So opposite is dy by dx. Okay, so now tan theta is equal to dy by dx. So d, keep it as it is, d by dx. Now instead of y, we have already used this, we have already derived this equation. So y, that is put it here, x minus 0.416 x square. Now solve this. Okay, so this would be derive this. Okay, so this would be dy by dx is equal to, instead of x, so it is 1 minus, so because it is square, so 2 into 0.416 into x. Okay, now this is tan theta. So tan theta is 1 minus 0.0832 times x. Okay, so this, still there is x in it. Now find out this x is nothing but at what distance you have to find the normal thrust and radial shear. Okay, now see here, they have asked us to find normal thrust and radial shear at a distance 6 meter. So x is equal to 6 meter. So at x is equal to 6 meter, so tan theta, okay, tan theta would be, put it in this equation, instead of x, put 6. So you'll get the angle here. So theta is tan inverse of 0.5, which is 26.6 degree. So once you get this theta, you have to use it in the formula now. So sine theta and cos theta. So sine 26.6, cos 26.6. Write this and keep here. Next is you have to use this here. So you have to find normal thrust N is equal to, okay, normal thrust N is equal to, we have already We already know this formula, that is V sine theta. So V and H should be constant. So V sine theta plus H cos theta. So we have already found out V. Now V is nothing but this force. You can see a vertical force, highest force you should take. So vertical force is 58, same it is. Vertical force, horizontal force. So 58.33, horizontal is 83.33. So substitute the value of sine theta, cos theta. You get normal thrust N. Similarly, radial shear Q. Okay, again, put this, solve this, write the equations properly, and then solve this, you'll get radial shear. So these are radial shear and normal thrust. Now, in addition to this, I think they've already asked you. Okay, normal thrust and radial shear at a distance 6 meter from the left, and right support, and 4 meter from the right support. Okay, they've asked you to find 4 meter from the right support. Again, the same thing. Usually in exam they'll ask you only from one support, but however you should know this. So calculate the normal thrust and radial shear at 4 meter from the right support. Again, same procedure, everything would be same. Everything would be same. See here, tan theta divided by dx, we've already found it as tan theta, but this time now x would be 4, because they asked to find at 4 meter. X is equal to 4 meter. Okay, and then put this value of x is equal to 4 and find out theta value. Once you find theta value, find sine theta and cos theta. Okay, now what you have to do here is, here the diagram here, right side, this is 141. See here, VA, here VB was 141, the same thing would be here 141 vertical, because from 0 to 4 meter, that is from right to 4 meter, there are no loads acting. Of course there is load acting after 4 meter, that is at the 4th meter, but from 0 to 4 there are no loads. So vertical force should be balanced by this vertical force, horizontal force should be balanced by this horizontal force. Okay, so once you draw this diagram, again same thing, tan theta is dy by dx. Okay, so now again solve this. Okay, now in this case here, 0 to 4, exactly at 4th meter there is load acting here. In the previous case here, at 8 meter from left hand it was acting. From 0 to 6 there was no load, but at 8 meter beyond this point it was acting. So we didn't consider any vertical force. But here what they was to find, this is 0 and this is 4. So at 4 meter only there is 150 kilonewton acting. So what we'll do here is 141.67, and there is a load of 150 kilonewton acting downward. You can see here 150 kilonewton. So now we have to consider both. We have to add this vertical force VB, okay, which is acting downward again. Vertical it is acting. The same VB is acting downward now. So 141.67 minus 150. So it would be now 141.67 minus 150 vertical. So whatever load is there, you have to deduct that. So 141.67 minus 50. So this is the vertical force which is acting. So you have to consider this here. So this happens only when there are loads acting between the spans. So that you have to check out carefully, and then again use the same formula, V sine theta plus H cos theta. So V would be now minus 8.33 followed by sine theta, and H would be same 83.33. So you'll get normal reaction, that is normal thrust, and the again same radial shear. Only different thing is you have to be careful with this load here. In whichever span, if they ask you to find out the N and Q, so in that span, if there is load acting downward, you have to deduct that load. So if there is no load acting, things become simple. Whatever is vertical force, same would be vertical upward, same would be vertical downward. If there are any loads acting in between that span which you're checking, so that load should be detected here. Okay, this is how you get normal thrust and radial shear. Okay, that's it for today. Thank you.